In this video, we'll explore the practical implementation of the 4-wire SPI communication between two EK-RA6M4 channels. SPI, short for Serial Peripheral Interface, is a communication protocol that enables a master MCU to establish communication with multiple peripheral or slave MCUs. While the communication can flow in both directions, it always begins with the master MCU. To begin, we open the E-Squared Studio. In a new workspace, we create a project called SPI_4W. As the device, we select the EK-RA6M4. We keep the default settings to flat project and executable build. For template, we select bare minimal. Once we click Finish, the project will be set up. In our application, we start by setting up some data that needs to be sent over SPI. We then copy this data into the SPI write buffer and send it through the master channel. The slave channel receives the data and stores it. After that, we make some changes to the received data, such as adding a constant value. Then we send the modified data back to the master channel and display it on the terminal. In the Renesas RA MCU family, there are two modes of SPI operation: the 3-wire, which is also known as clock synchronous operation, and the 4-wire, which is also known as the SPI operation. For the 3-wire mode, the slave select line is not used. To establish the transmission process, we begin by adding two SPI stacks. One is configured as a master and the other as a slave. You can find these stacks in the connectivity section of your project. Name the master channel G_SPI_master and enable the interrupts. Additionally, we rename the callback function to SPI master callback. The SPI mode is set to SPI operation, which is the 4-wire mode. We also select full duplex for bidirectional data transfer. We set the bitrate to 9600. The pins are already pre-selected based on the SPI channel. We then add another SPI stack for the slave channel. We name it G_SPI_slave. We rename the callback function to SPI_slave_callback. The bitrate is changed to 9600 to match the other channel. The operating mode is set to slave. We then look into the pins associated with this transmission. We can make changes to the pins associated with each SPI channel. The 4 pins are already pre-selected. We then check the same for the SPI1 slave channel. We then generate the project contents. For the connections, the master channel uses the pin 202 as MISO, pin 203 as MOSI, pin 204 as the clock, and pin 205 as slave select. As for the slave, the pins are 410, 411, 412, and 413. We will now open the hull entry file to start coding. The SPI call functions are already available under the developer's assistance. To print out on the terminal, we can make use of the Segger library. The files can be downloaded from the Segger RTT terminal website and need to be copied to our source folder. We will add an additional header file here, and we will include that in our source code. In the common utils file, we have all the macros related to the Segger library. We will then define some constants to be used in our program. Then we will declare the SPI event flag variables. These flag variables are of custom data types and are defined in the FSP SPI library. We will declare the 8-bit unsigned integer arrays for the transmission and reception buffer, and we will also declare a variable to hold the length of our data transmission. Now, we will define the callback functions. We have defined the names of our callback functions in the stack properties. From the developer's assistance, we can already get the call definition for each SPI channel. In the callback functions, we shall store the appropriate flag events in the respective variables. Now, we move on to the main body of the program. We start by declaring and initializing the FSP error variable. The first step for SPI communication is to open the channels. We can call the SPI open function from the developer's assistance. We also add the assert macro, which ensures that the return status for the function calls are successful before proceeding to the next line of code. We initialize the input data as an 8-bit unsigned integer with a value of 0. We also specify the number of bytes to be transmitted to be a single byte. Then we create a while loop. In the while loop, we first copy the data to the transfer buffer and then print this input in the terminal. To begin data exchange, we will need to pull the slave select line low. We do that by I/O operations. We then execute the SPI write function to dispatch this data from the transfer buffer. We also use the assert macro here. Then we change the arguments of the function to include the address of the source, which is the transmission buffer, length of transmission, the variable num bytes, and bit width, which is 8 bits. Then we insert the function call for reading data that has arrived to the slave channel. We store this data in the slave receive buffer. In this case as well, we specify the length of transmission and the bit width. We will then insert a while loop to check for the SPI event flags. These flags are set by the SPI callback functions once a SPI transmission or reception is completed. The while loop will exit once both the transmission and reception are completed and relevant flags are set. Once the while loop has exited, we will pull the slave select pin high and then we will reset the flags. We will also print a confirmation to the terminal regarding the successful data transfer. Our next step is to modify this input. We conduct a simple addition to this value. Then we send this modified value back to the master channel. We implement the same procedure as before, only this time the slave is sending the data. We reset the SPI event flags after the transmission is completed, and then we print a confirmation on the terminal. We also print the output value, that is, the data that was received by the master buffer. We will then increase the initial value by 1 and add a 3-second delay, then end the while loop. The loop continues by sending a new value from master to slave. The program can now be built. Once build is completed without any errors, we can upload the program to our board. We need to find the address of the Segger block after the program has been compiled. This value is required to connect with the RTT terminal. Once we run the program, the output is displayed on the terminal. In each instance, the input is increased by 1, and the program adds 2 to this when received from master channel and sends back the updated value. We have now demonstrated the use of a 4-wire SPI communication on array microcontrollers.